Hello, everybody, and welcome to the Toronto Geometry Colloquium. This is a weekly web series all about geometry processing.
This colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities.
Every week, we'll have an opener talking about their cutting-edge research for 10 minutes, followed by a headliner giving us a keynote presentation.
And this week is very, very special. So unlike our past speakers, this week we have two fantastic speakers from the mechanical engineering department. But the cool thing is that they also work on the similar problems such as shape optimization and fluid dynamics. So our opener, Isabel Scherl, is going to talk about robust modal decompositions of fluid floats. And our headliner, Professor Burak, is going to talk about neural topology optimization for additive manufacturing and power plant design in electronic circuits. So if you have any questions, please leave those comments in the YouTube chat. So first, it's my great pleasure to introduce our opener, Isabel. So she's a PhD candidate at the University of Washington, advised by Professor Brian Pelage and Professor Steve Brunton. So Isabel's research focuses on experimental fluid dynamics. So in other words, she not only cares about figuring out accurate simulation models, which is what we care a lot, and she also cares about verifying these simulation models with real experiments so that they can be used in real-world engineering problems. For example, the one I like the most is on her design of the cross-flow turbine, which could be a very promising renewable energy solution to harness the power from the ocean. So today, we are very lucky to have Isabel to share about her research on fluid modal decomposition. So please take away, Isabel. I think you're muted, Isabel.
I sure was. Okay, am I good to go? Okay, well, thank you for the introduction and for the opportunity to share my work in this avenue. Today I'm going to be talking to you about robust modal decompositions for fluid flows. So this is a really exciting result that I'm sharing with you, and I'm going to be talking about how we can leverage data-driven methods to improve our pattern recognition in experimental flow fields. So this work would not have been possible without my collaborators and funding as well. So first, I'm going to talk to you a little bit about modal decompositions and specifically POD or PCA. So POD decomposes, or proper orthogonal decomposition, also known as principal component analysis, depending on which field you're in, decomposes a flow into modes ordered hierarchically, where the first flow is the mean field and the subsequent modes are all 90 degrees out of phase with one another. So they're sort of matching. And each one of these, if you add them back up, you get that resultant original flow field. So this is a really efficient way to represent our data. And it's a really sort of the first way that people tend to do pattern recognition in their data. So this is all well and good, but a lot of our flow fields, especially when we're looking at actual experimental data, they don't look like this beautiful, clean flow field. Maybe they look like this. So this is sort of that original data matrix that we have when we're actually looking at measured fields. Of course, this is a simulation with added noise. This is a simulation where individual pixels have been selected and changed to be very large or small. This is called salt and pepper noise, and it's actually somewhat representative of a lot of the noise that we see in our experimental data. So what we want to do is break this flow field down into the low rank, patterned, coherent, structured data, the actual patterns that exist in our data, and isolate that from the sparse noise. So this is inherently, we're looking at this problem of fixing our flow field data as a pattern identification problem. And the way we want to do this is using a method from robust statistics called RPCA, or Robust Principal Component Analysis. And robust principal component analysis can identify low dimensional structure in data. So this is an example from the original paper by the original authors. And in this example, they have the eigenfaces. This is the example, well, one of the examples that's presented is eigenfaces, and the nose and mouth, eyes, nose, and mouth, all of the faces in the data set have that. And what they want to do is identify this sparse noise from this low rank structure. So the low rank structure is the flow field, and this disguise is our sparse noise. So instead of removing a disguise, we want to identify our patterns in our flow field data. So when we want to do this, the way we do this is that we want to solve this optimization. This is a non-convex optimization where we want to minimize the rank of L because we want that to be as low rank as possible, and promote sparsity in S. Since this is non-convex, we actually relax this to the following, and we introduce this hyperparameter lambda. And the hyperparameter lambda is a scaling parameter for our data set. And this is because a lot of times when we're actually looking at data, it's not perfectly low rank data with perfectly sparse uncorrelated noise. A lot of times in actual experimental data, we see correlated noise, especially in the regions of interest where there are interesting three-dimensional dynamics. So ideally, lambda equals 1 as presented in the original paper, but we are introducing this lambda naught parameter as the scaling parameter. Okay, so if we want to look at how this lambda parameter affects the results of the decomposition, we can have this flow field. If we make lambda too small, the rank is too low, all of the data is allocated to the sparse matrix. If we make it too large, the opposite happens, the rank is too high and there's no noise reduction. But there's this happy middle ground where we get this perfect bisection of, or nearly perfect bisection of low rank structure and sparse noise. This is great. This is sort of exactly what this algorithm is meant for. This is very low rank data and very sparse uncorrelated noise. But let's say instead we bias the noise towards regions of interesting flow dynamics. So let's say we bias them where the flow is rotational. So in regions of high vorticity, then you can see that we still get a really nice bisection at that optimal lambda value. We're seeing really nice noise reduction. And the reason there's structure in the sparse space is because the noise is correlated, the noise is structured. And this is great, but what we were talking about is we wanted to see, wasn't just noise reduction, it was looking at pattern recognition or modal decompositions. So if we do this, if we do a PCA modal decomposition on both the data matrix and the low rank structure, this is what we see. So these are the true modes to compare our baseline comparison. If we do PCA on the data matrix with all of the noise, we get this. In the first mode, you could maybe argue that you can see the mean field a little bit, but really it's mostly incoherent. And this is just for 2 full cycles of vortex shedding. So if you add an additional, if you do PCA on the low rank modes, so you take the modal decomposition of that low rank data set, you get a much better result. You can actually see structure in the modes, but they are a little noisy. If you increase the amount of data you're using from 2 periods to 5 periods, the PCA result doesn't change very much. The data matrix decomposition is still quite messy and incoherent, but the L matrix decomposition actually looks pretty good. So if we look at this more qualitatively, you can see that even with a small amount of data, we still get a really nice modal decomposition. But as you increase the amount of data, it gets better and better. And that's really great. That means that we can perhaps you get more out of small quantities of data when larger quantities of data are too expensive to acquire. So if we look at the discrete time DMD eigenvalues, so these are eigenvalues from sort of performing DMD on our data. If we look at them for the data matrix on the left, the red, the plot with the red crosses, you can see that most of them are clustered around the origin. That means that these modes are highly damped and that their dynamics are not evident throughout the time series. And whereas the RPCA modes are pretty much matching the true modes, and they are demonstrating their persistent oscillatory evolution in time. And that means these modes are undamped, and also they are matching the original true data matrix. So this is great. This is a cylinder. This is flow past a cylinder with artificial noise. Let's say we want to look at a real data matrix. We get a really similar result where the we want to look at actual data. This is what actual data looks like, actual experimental data. If we make the rank too low, if we make the lambda value too small, the rank is too low, and we see a lot of structure in the sparse. Lambda too high, rank is too high, and there's minimal noise reduction. And there's sort of this middle ground where you're balancing these two different things that you want to be, you want good noise reduction, but you still want all of your evidence structure. So if we look at the PCA, if we look at the PCA modes, you can see that if we have our lambda value too small, those modes are not resolved at higher mode numbers, and they get higher resolved as you increase your lambda value. And we think that this can be, by looking at the singular values, that this can be used to choose your lambda value in an actual experimental data set. So the last example I'm going to show you is something that's actually really close to the research I do. It's on vertical axis wind turbines. So it's turbines that rotate about an axis that's perpendicular to the free stream flow. They look like this. They have this nice bubble visualization, and we're going to be looking at a frame that is just a bit downstream with structures convecting through. So this is the processing pipeline that the two-dimensional flow field data that we collect looks like. We start with image pairs. We do a cross correlation to get a velocity field. And we have a lot of missing measurements. Each one of these white dots in this pipeline is a missing measurement. So after cross correlation, there's a vector validation step. And then from there, you do a local interpolation. It's very hard to locally interpolate when your missing measurements are localized to certain regions, because if you don't have a lot of local information, local interpolation isn't that useful. So instead, what we're proposing is that you use a global technique instead of a local technique. And if you use a sort of RPCA instead of an interpolation, you get a really similar phase median field. So that means we're getting similar results. But where they deviate is if you look at the phase standard deviation. So for the standard deviation of the interpolated field, there's these like dark spots, and those are sort of where there's inconsistent interpolation. Whereas for the RPCA, you get this sort of smooth topography that's likely associated with the turbulence in the flow field. So with that, I want to thank the organizers and pass it off to Burak.
Thank you, Isabel, for this fantastic talk, and this is the results really beautiful. So as usual, we will proceed to the talk of our headliner and have a joint Q&A near the end. So now it's the time to introduce our headliner, Professor Kara from the Carnegie Mellon University. So his research covers a wide range of problems in computational design and additive manufacturing. He's also the pioneer in developing machine learning solutions to mechanical engineering applications. So his massive contributions also made him the recipient of the prestigious NSF Career Awards. So Professor Kara also plays a very important role in my research career because He was actually my advisor during my master's degree. And he's also the advisor who introduced me to this field of geometry processing and the first teacher who taught me how to do research. So without him, I won't be here. So it is really, really my great honor to introduce Professor Kara at this colloquium. So without further ado, please join me to welcome Professor Kara.
Thank you very much, Derek. That was a really nice introduction. I really appreciate that. Let me share my screen. And hopefully my presentation will be right now visible.
Yes, it's visible.
All right, great. Well, good morning, everyone. So in today's talk, I thought about presenting two recently completed projects, still a few pieces that need to be further developed. But instead of having one topic to cover, I thought about maybe doing two little mini project introductions. So the first one is on neural topology optimization for additive manufacturing. And our team consists of Ray Chen, Aditya, Professor Kate Whitefoot, and myself. And we're presenting this very recent work, which is to be presented at the ASME IDTC Design Conferences this summer. So the motivation behind this work is to do simultaneous part design and support structure minimization. So support structure is a very big problem in additive manufacturing, especially in metals additive, where in order to prevent shape deformations or be able to support a net part as it's being printed, you need to construct structures that are eventually sacrificial, which are the support structures shown here. But these can be very time-consuming to print. They use expensive powders, and eventually they will have to be removed as shown on the right-hand side. So there is a tremendous incentive to minimize the amount of support structures used as we're printing these structures. So what we are trying to do here is do three things all at once so as to minimize the needed support structure. So we are doing conjoint topology optimization, part segmentation, and for each segment, optimize build direction computation. And on the left side here, you can see the problem definition where we have a design domain for which we want to generate the structure shown on the right. Here, we are trying to optimize or minimize three different objectives. The first objective is the compliance of the structure. The second one is a target volume fraction, meaning that we want to remove, let's say, 80% of the initial mass. And the final one is the amount of support structure. So all these disparate objectives have to be jointly minimized in order to create the shape on the right. However, what you're seeing here is not a monolithic shape. The user has also said, we are open to segmenting the part into three different partitions. And why do we want to use partitions rather than monolithic designs? Because they can tremendously reduce the amount of support structure needed as shown here. So basically, we're formulating a problem in which, given what's shown on the top right, we want to be able to create a final design where the part geometries, the topologies, are automatically designed and they're taken into account the total amount of support structure that will be needed. And as shown here, if you were to print the part without actually partitioning, you would be using quite a bit of support structure. Whereas if you do both topology optimization as well as segmentation and part build direction optimization, you can see that amount of support structure can be significantly reduced. So we are building on quite a bit of existing work. There have been quite a few recent works in combining neural approaches, not data-driven necessarily, but neural network optimization schemes to do topology optimization. And this is a seminal work in our field and one that we completely agree with in terms of the approach and the formulation. There have been others that are looking at, for instance, overhang angle control to minimize the amount of support structure. Our previous work in this group has also looked at part segmentation consolidation as a way to accelerate and make additive manufacturing more affordable. So we have been looking at different combinatorial problems in which we choose the subset of parts that need to be maybe printed together versus those that need to be separated. Likewise, a lot of data-driven approaches have been proposed to date, in which the approaches would sample across different boundary conditions so as to learn a way to do real-time topology optimization based on previously obtained training data. Other more recent works are looking at using neural networks as a replacement for finite element analysis to do compliance calculations, displacement calculations, for instance, all through a neural network. And finally, there are commercial interests in creating structures that minimize, for instance, the support structure needed and modify the geometry accordingly. So our work, as I said, builds upon all these works. And this is basically the major architecture we have. And it consists of three important modules here. The first one is shown on the top left, which is the topology network, whose job is to actually create a shape hypothesis, something that's shown on the right-hand side here. So alongside the same network is what it would call a segmentation network that shares quite a few similarities in terms of the input structures to the two networks. However, its job is quite different. Its job is to do a classification or a segmentation on the final density field. And finally, we have a print angle network that will take the results of the segmentation network, and for each segment that has been produced, it will automatically determine the best print direction in which it should be printed. So all these networks are working together where we are trying to minimize a combined loss function. That loss function is a function of the compliance, which is coming of a finite element analysis, as well as other geometric considerations, as I said, the overhang, for instance, the undercuts that need to be minimized so as to overall minimize the support structure. So these all need to work together in a differentiable way and jointly in order to produce this simultaneous topology optimization and part segmentation. So the topology network is building on a recent work that was published, as I mentioned. And recently, I think in this symposium series, there was a very nice talk by Nikon on using Fourier layers for featurizing the input space. And the structure is remarkably simple. Here, what we have is a voxelized space in which we sample XYZ spatial coordinates. And for each one, we actually featurize it by passing it through a Fourier layer, from which we connect the outputs of the Fourier layer across different spatial frequencies to create a dense layer, from which a final density is produced at that given coordinate. So we have now a relationship between a coordinate XYZ as input and the resulting density that will be used for doing material hypothesis. Likewise, a very similar structure is then used for segmenting the part. So the segmentation actually takes into account similarly the XYZ coordinates from a given original unoptimized domain. We extract these voxel points and then we pass it through a similar layer, but we do a classification at the end to get a class label for each voxel and each density value. And finally, we do print angle optimization on each one of the segments that have been created out of this middle network. So all these three together are assembled in order to attain those three different objectives. So the topology network is building on existing work in which we create a network where the finite element analysis is giving us a compliance value. Compliance is nothing but the inverse of stiffness, basically. And what we're trying to now establish is a gradient, analytical gradient between the compliance, the final compliance as an engineering performance, relative to each one of the voxel density values. And that there's an explicit analytical expression for that, which we directly tap into, which is fantastic. Other things that can be easily done here is to enforce passive elements, meaning regions in which our solution cannot exist. We are enforcing that with an L1 loss on the masked regions. Also, symmetry is very easy to impose on these types of structures using very simple tricks as shown here. The more interesting part is the overhang identification, meaning can we quickly and in a differentiable way determine how much volume there is going to be to be accounted for so that we can feed that information back into our earlier stages for better material hypothesis. So this is also done in a way that takes advantage of auto differentiation. In this case, we have a neural network, which is shown as T here, which takes coordinates as input and produces a density field. So using a gradient tape, basically, we can actually obtain the gradient of the density field relative to our input coordinates very easily. So this comes directly out of the construction of the network architecture. Now, with this information, what we can do is impose known constraints and opportunities in additive manufacturing. For instance, we use heaviside filtering, similar to how our colleagues, other colleagues have done in the past, in order to impose build angles. So in additive manufacturing, you can actually create slanted builds that are not going 90 degrees perpendicular, but can actually build upon the previous layer while actually moving to the side. So this is called the build angle. In our case, we're using a 60-degree build angle, meaning that as long as you're within that 60-degree angle, you will not need support structure to support that part of the net shape. So we are using these types of filters to then look at how the density field combined with the build direction can lead us to determine what parts of the final design will eventually be supported. For instance, in this case, the red piece and the red dot here will be the ones that actually require quite a bit of support structure. But we're not only finding the surfaces, but also the total amount of volume that falls under these overhang regions. So we do what we call a height penalized overhang determination, where we determine eventually this H alpha, which is a surrogate for the total support structure that will be needed. This is not a very high fidelity approximation, because support structures don't use the full volume. They actually create some sparsity in the structure, but it nonetheless works as a very good surrogate for estimating the support structure. Finally, all the computations are put together into this loss function, the compliance, the volume fraction as a target, and the support structure that needs to be used. And we are trying to minimize this as shown here. So FEA for compliance, and segmentation and the print direction optimization for overhang, all of that gets fed into the loss function, all in a differentiable way. Now, using this, we have observed interesting trends here. For instance, if you were only to look at the surface areas that needed support, you may actually produce structures of this sort. So they have a reasonable compliance, let's say around 42. However, this does not take into account, for instance, the high region here, the volume that needs to be supported with material. However, if you add this constraint of height panelized overhang detection, we can actually truly minimize that objective, going from 0.12 to 0.008, while not compromising on the compliance significantly. So we are really trying to now study the impacts of these types of trade-offs by doing these three different objective minimizations jointly. Here's another example of a simple structure, fixed displacement boundary conditions, a load in the middle. We have the specifications for the engineering problem. We are requesting 2 segments. You can say 1, 2, 3, however many segments you desire, and a final structure comes out of this. But note that the segmentation is not done after the network topology has been finished, right? So these are done simultaneously. So the structure that actually gets optimized, when you actually print it, you will see that there's almost no support structure that's needed, because the part segmentation actually breaks the part into 2 right down the middle, and each part can actually be reoriented, and that best reorientation is determined by the network. And the design of the structure actually meets the minimum build angle nicely, so that no support structure will eventually be needed in order to print this. You may say, well, there's an assembly part to this, which is accurate, and I'm going to get to that point in a few minutes. Here's a slightly more complex example with masked regions, as well as a number of 3 segments that we're targeting for. And here's the final structure that was optimized, together with all the partitions that come out of it and their optimal build directions. So for each part, it actually tells us in which direction we should be building this. And you see that in all three cases, for each three segments, the amount of support structure will be very, very minimal. And we can see that we can monitor that progress throughout the iterations by monitoring the compliance, the overhang support structure, and the angles that are being produced here. So the major takeaways from this work is, except for the FEA solver, for which we have an analytical gradient from the compliance into the densities, everything is handled through automatic differentiation. So this makes it very modular, very easy to expand and add new constraints and objectives in the upcoming months and years. We did our own FEA solver using a CUDA accelerated sparse iterative solver, and this is working remarkably fast. The major part, the major bottleneck in this is basically the amount of voxels that we use for the training. So the more voxels we have combined with the Fourier, we're running into some RAM issues, but the entire pipeline can be run without any additional library installations on Google Colab. Some challenges and opportunities, as I said, the neural network architecture actually requires heavy use of the video RAM. So we are now thinking about doing a mini batch training rather than a full batch training of the voxel space. Hyperparameter tuning is always a major issue, still not optimized, but we're working on that. Finally, we want to extend this work to generating what is conventionally a subtractive machining part, meaning topologies that are more conducive to machining rather than additive manufacturing. So these will require us to think about what are the constraints in 3-axis CNC, 5-axis CNC, where additional considerations need to come into the picture over what additive manufacturing typically tries to do. Finally, assembly surface design is going to be an important part, where we are currently assuming that once these are disassembled and printed separately, you can actually easily join them. But that's still, not physically 100% accurate, because you have to consider, how are you going to join these? Is it going to be welding? Is the material properties going to be, consistent with what you have assumed, and so forth. But nonetheless, this gives the designer, I think, a good start into thinking about how to partition the space and optimally create each topology to minimize the support structure. So with that, without taking any questions, I really want to jump into a completely different project. This is the automatic power plane generation with genetic optimization and neural networks. Again, we have a large team of collaborators here, mostly from Carnegie Mellon, as well as the Cadence Systems, which is the pioneer, the industry leader in electronics design automation. Again, this is a work that has been recently accepted to an ASME IDTC conference, which we will be presenting sometime this summer. So the problem that we're faced here is the design of what are called power planes in printed circuit boards. And these power planes are part of if you think about the entire EDA pipeline, this pertains to the physical design of the board, in which you need to lay down and design these what is shown as green planes. And these planes actually are metallic planes that carry various power levels to power the signal nets, as well as ground nets for grounding the your voltages. And on a given circuit board, there could be multiple levels of powers, meaning that you're not looking at just two planes of 5 volts versus 0 volts. You have multiple layers of these power levels. So you need to actually construct multiple different planes. So the way that this is presented to a design engineer is basically in the form of colored pins, as you're seeing here. In here, what we have is a group of pins colored uniquely that should belong to a unique plane. And then different colored pins should be belonging to distinct planes. That is, we should not have overlapping planes, touching planes. These should be all mutually exclusive planes. However, this becomes a remarkably difficult problem even for seasoned engineers, because this involves a very manual and tedious process of being able to segment a plane that's shown on the right. We're showing a rather simple case, but I'm about to show you a case where we tried this with multiple engineering students, and they had a hard time actually finishing the task. But other things that actually give rise to the shape of the power planes are what are called the IR drop or the voltage drop, and other things that need to do with the multi-layering through vias and other considerations that eventually shape the power planes that we're seeing here. So our goal in this work is not to do the detailed power plane design that you're seeing in the middle, but at least do a rough cut in determining the power plane topologies, the connectivities, so that detailed design can actually take over after those topological planes have been determined. Here's the challenge example that we posted to a group of students here, where we gave on a piece of paper this board, basically the one that you're seeing in the middle, with multiple different nets, meaning that each net has a number of pins that are colored uniquely, and there are multiple different nets, meaning multiple different colors. And the challenge was, okay, can you now create planes that actually overfit to a particular net and does not actually take any pins from all the other nets? And here's one typical solution that is shown on the right. You can see that, as the answer is given, it's not too difficult to agree with the solution. Yes, this is a reasonable solution, but given the middle one, it is a very heavy trial and error process in order to get these planes right. So what is our goal here? So we want to create M mutually exclusive power planes where M is the number of nets. Each net can have many, many pins, and we want to be able to group those pins correctly. So you can think about one net corresponds to one power plane, and we may have M of these. So the major goal here is to minimize what is called disconnected islands, because you could move it to the extreme and you can create a little plane around each pin and call it a day, right? But the goal is to pour a single metallic connection, meaning a single island that will serve as a single plane. And it's very desirable that you have a single plane rather than multiple disjoint planes for a given net. So you want to use a single plane that to combine all the pins coming from a single net. And we also need to have a perfect classification scheme, meaning that we are not going to be able to accommodate any misclassification. So we have to have mutually exclusive planes where the segmentation accuracy is always 100%, because all of a sudden you will create an infeasible design in which a pin that should belong to a different net would be touching a wrong metallic plane if this was not truly 100% accurate. So just to talk a little bit about, I know the setup took a little bit of time, but in terms of what is a feasible design versus a desirable design. Here you're seeing examples of infeasible designs because there's the red net and then there's the blue net, and there's definitely misclassification, right? In the first one, this red is misclassified, this blue is misclassified. In this case, this blue triangle is misclassified. It should belong to a blue power plane. This is a feasible design. Two designs that we're showing here are feasible, but these are undesirable. So the classification is 100% accurate, but it is undesirable because it actually creates multiple disjoint planes for the red net. Likewise, in this example, multiple disjoint planes for the blue net. So this is actually an undesirable but feasible solution. Here are some examples of both desirable and feasible solutions. And you can, I think, appreciate that simple approaches to image segmentation based on your favorite ML technique will have a hard time actually enforcing this single connectedness using simple regularization techniques. So it is not about smoothness necessarily only, it is also about actually walking through very, very long chains in order to connect disjoint and far apart pins together using a single metal plane. But there are other goals like large margins. We want our boundaries to be as much as possible away from the pins so that there's room to operate for detailed design. We want smooth boundaries and low IR drop, meaning that low voltage drop, which means that we want to avoid necking in these solutions. In this work, we are not concerned about the voltage drop yet, because that will be a shape optimization. We're now trying to find the correct topologies first. Okay, so how do we do this? I think you can all appreciate that there are many ways of approaching this, but the way that we have taken after trying and failing on a few others is the notion of using handles as free and movable, evolvable handles or parameters that can shape a power plane, a board. Basically, what we have is a set of pins, in this case lettered as A, B, C, D, each letter belonging to a particular net. These are static, these are part of the problem, but alongside that, we instantiate handles, labeled handles, each belonging to one particular net. So a net may have a number of handles that will give that degree of freedom to shape the board. So given the static pins and the mobile handles, what we want to do is we want to be able to do classification, segmentation of the image, in which we take the labeled handles as well as the pins as input. Then we do our geometric calculations on contour detection, distance calculation, and then from there we make a judgment on how to improve, see how many disconnected islands are there, and minimize that. All of this is currently done through a derivative-free approach using genetic optimization, but I think with more work, there might be opportunities to do this in a differentiable way. We are currently exploring that avenue also. So how does the MLP work in this case? So given the board and the current hypothesis of the handle placement, the circles that are movable, given this current configuration, it actually does a classification where the goal is to terribly overfit to the given data, because we want zero misclassification on the pins that are shown here. The data, input data, consists of the pins as well as the handles, but the final classification is only determined on the pins. Basically, that's what matters, because the handles are an abstract notion that we impose on the problem. So given this input, we pass it through a feature expansion layer, through augmentation, and then through a 3-layer neural network in order to create a cross-entropy loss that is being trained live in a dynamic fashion. So given this board, it will create a segmentation that's shown here. So given that segment, then we evaluate the quality of this. We look at the number of disconnected islands. That's something we want to minimize. And in order to do that, we have to have a mechanism, a gradient, a force that actually shapes these. So the types of geometric computations we do are the distance between disjoint islands, how can they be put together. So we turn all of that into objective functions that need to be minimized. And here you're seeing a few examples of if we were to use just straight neural network versus using the genetic optimization to further shape the planes that are suggested by the neural network, you're seeing the differences. In this example, for instance, plane E has 2 islands, which is undesirable, but through shaping, we can actually now connect those 2 disconnected islands into one. Likewise, you're seeing here certain shapes that are disconnected. For instance, the yellow D net is actually disconnected, but through the genetic shaping, we can actually now start connecting those disconnected islands. So this all works towards minimizing our objectives. And we can also monitor the evolution of the solutions as a function of the iterations. We get a bundle of solutions that can all be feasible, but they might have slightly different qualities in terms of desirability, and that's what I'm going to focus on next. But basically, in our hands, at the end of this, we have a bunch of solutions that are all feasible. As a way to compare this work to this approach to our previous attempts, we actually started with a completely different approach involving minimum spanning trees and A-star routing, and we use that as a baseline where, given the bare board, we actually created minimum spanning trees that fully connect all the pins for each net. And then we actually looked at intersections and created disconnections, and then finally used methods like reinforcement learning or other approaches to A-star search to join the disjoint trees. This was a very, very heavy approach, very time consuming, but it did accomplish, at least got us close to what we expected. Nonetheless, it was not very good at minimizing the total amounts of disconnected islands because there was a combinatorial nature to choosing which tree should be cut off first, compared to the others. So that sequencing actually made this problem a very difficult one to solve optimally. Anyway, just to compare, our initial attempt to what we have currently, achieved. At the top, you see what our current system does with the MLP and Geo working together. EI stands for extra islands. The smaller, the better. 0 is ideal. You're seeing such a solution here, but using the A star with the minimum spanning tree, you can see that the bottom row has actually worse quality compared to the power planes that are generated at the top. We also compared, a head-to-head over a large group of solutions, and about 71% of the time, we saw that this genetic approach actually outperforms the A star approach. The lower, the better in terms of the extra islands. So the horizontal axis is all the 130 different examples, designs that we simulated, and in pretty much a large number of cases, this genetic approach actually outperformed A star. However, we also noticed in our first attempt that the boundaries of the final planes were not always desirable. Sometimes it created very long, non-smooth, and small margin boundaries, even though they were feasible designs and desirable with 0 extra islands. The final results were less than satisfactory. So what we observed is the need to impose additional constraints, some differentiable, some not differentiable, in order to shape the boundaries a little further. And we are using additional quantities that are coming from, for instance, a distance transformation matrix of the original pins and being able to read off values as we're creating the boundaries. So these maps, underlying maps, actually help in the shaping of the final boundaries. Here's an example of the additional objectives at play. Here's an initial generation or initial solution coming out of our original formulation. But if you start imposing a penalty on the boundary length, for instance, this being a long boundary, we want short boundaries, it starts to change the shape as you're seeing here. If you're saying that we want to be as far as possible from the pins, you will resort to the minimum spanning, the distance transform matrices here so that your system is as far as possible from the pins. However, it can become greedy in which it tries to move away from the pins as much as possible, but not in the most efficient way. It basically does a random walk in the space in order to accumulate all the numbers that it can to create a lot of zigzaggy solutions. And finally, if you now balance the weights of boundary length minimization as well as margin maximization, you get more reasonable results in terms of the final solutions. And we are currently in the process of now imposing these additional desires into the formulation. And we are now getting more, I think, what I call suitable, acceptable decision boundaries compared to the old ones. For instance, in this case, you're seeing that there's a long boundary that's created just for these 3 pins here, but a more meaningful one would be simply a circle that we're seeing right around here. So we are, I think, cautiously optimistic that through this approach, we can now move this into the real world scenarios in which multiple layer power planes need to be created. So you're not only considering the plane generation in a single plane, but there might be multiple parallel planes in which all planes are at play. We want to add other performance-related considerations like the IR drop minimization so that you don't lose a lot of energy or signal through this metal plane. And finally, the detailed design and the via placement that is connecting metal planes across different layers will be necessary. Thank you very much, and I appreciate your time.
Thank you both for the great talks. And we'll now move to our joint Q&A session for both speakers. And in the meantime, if you have additional questions, please feel free to leave them in the YouTube chat. So first, we'll give Burak like a short break. We'll start with a question for Isabel. So Isabel, so like the first question we have is related to the PCA. So are you here, Isabel? Oh, yeah, okay. So PCA kind of implicit assumes that like the data you work on can be kind of well reconstructed by linearly combine those principal components. So we are wondering like whether this kind of linearity assumptions is valid for general fluids. Do you think something like nonlinear PCA could works better for like a better reconstruction or something?
Sure, I think that's a good point. I do think that even if it's not considered valid, it's used with extreme regularity, and that it actually does quite a good job in a lot of cases. So, I mean, I think there's this long history in fluids of people using techniques that are meant for linear systems and using them in nonlinear cases, and we get really nice results. So, yeah, some techniques that are meant for linearity maybe sometimes better suited, but also these really simple ones tend to give us pretty good results as well.
That's very good to know that classic techniques are very useful, and we know that how well we generalize to other things. And another follow-up is that it's actually a more like clarification question. So in your method, do you need to recompute the PCA basis for every new things? For example, you have like a cylinder, if your water flow from like left to right, and if there's a new thing like from right to left, for example, do you need to recompute those PCA bases, or can you actually reuse those bases?
No, you recompute them, but it tends to be, unless your data set is enormous, it's not very expensive. And usually it's pretty quick.
Okay, that's good to know that this is not like a bottleneck. Okay, the next question is for Professor Kara. So as you mentioned that Nikon's work used like the neural field architecture on those topology optimization, and we're wondering like what would be the pros and cons comparing to the architecture you use, like the voxel-based architecture, and those kind of more like continuous kind of neural network representation. What would be the pros and cons to choose the architecture in the context of topology optimization?
Right. In Nikon's work, I think the primary focus was on the Fourier layers and how to really, make good decisions on the spatial frequency of the information. So I think these are not two alternatives. I think everything that we have done could definitely leverage all that work. I think they're doing sub-voxel level detail generation with their networks. All of that is really at play here. I think our difference or our contribution to the community is the ability to show these composable networks that each operate independently, can be turned on and off independently, and will do, independent print direction optimization, independent segmentation, and independent network topology optimization, and being able to join them all together in a differentiable way to produce the output. I think these two approaches are complementary. In terms of the architecture choice, I think there's quite a bit of room for ourselves to optimize the details of our architecture. For instance, we immediately see that the VRAM is a major issue. This may be solved using a mini-batch approach on the input side, or playing with the architecture a little bit more to be a little bit more selective in our Fourier feature expansion, for instance. So we may not need a long vector of Fourier, which I think we're using 3000 by 1 vectors right now. We may not need that many. So I think a little bit more thought and principled approach to the details of that could benefit our work for sure.
Well, thank you for this really detailed answer. It's nice to know that like these techniques can combine together and make a better solution. And the next question is actually related to this, but this is more like a meta question. So because that like from a person like who are not working on like neural network topology optimization, we just feel like there are so many papers proposing like very promising solutions to solve this problem. But in your opinion, is this technology are ready to be used to replace those traditional like topology optimization pipeline, or actually there are still some big bottlenecks that prevent us from using machine learning solutions for this problem?
So I can answer that in two ways. So one is the general feeling about topology optimization, how it's used in industry. Many times, if the major problem in industry is not so much the topology optimization software, the approach, it's really, can the end user use the technology effectively? Can they set boundary conditions effectively? Do they know how to set up the problem? Do they know how to post-process results if necessary? How do they impose knowledge of the manufacturing techniques they will use into the topology optimization? These are really the big questions, I think, in making topology optimization industrially relevant. There's a tremendous amount of work that is still ongoing on. In that picture, I would say neural network approaches are very, very competitive. I mean, I see really no limit or weakness in neural network-based approaches to topology optimization over conventional MMA-based, optimization techniques in SIMP or in level sets. The other piece to this, however, is the question of machine learning driven approach to topology optimization, because that's where I want to distinguish between a data driven approach versus a direct approach. So we have published in the past data driven approaches in which you would actually learn from past designs, past topologies by sampling your boundary conditions. I personally believe that that is not a productive direction. Instead, neural networks that actually are specifically trying to solve a given specific problem with the given boundary conditions are more productive. I think those are not going to be limited by, how well did you sample your boundary condition space, how well you can, scale it up. Those are not going to suffer from that. So our current presentation, which I just talked about, is moving towards that, meaning creating a neural network that can overfit heavily to the data that's being presented many, many times. So in that regard, I truly believe that the neural networks are just as good as existing methods.
Wow, this is really good to know. And I'm looking forward to see how this approach will change topology optimization probably in 5 years or 10 years. So now let's circle back to the question for Isabel. So there are some questions this is actually related to some research in our fields, because in our field, a rendering, a lot of people use use very low samples to render a noisy image and use machine learning to kind of denoise the image, and the result looks pretty impressive. We're just wondering, in your case, do you imagine a machine learning denoiser could be used to kind of denoise the fluid data you have? I think you're muted.
Yeah, absolutely. I think there are a lot of promising techniques. It's a very broad question that I think there are a lot of promising techniques that could be used for denoising. It's a really rich space, and there's a lot of techniques. We actually use, I do a lot of experimental acquisition, and we use filtering and other things when we're just trying to process our data, just because data is noisy. And I think that can be often overlooked when you're dealing with simulation or, other types of sets.
Okay, so actually we have another follow-up to this is that actually related to the filtering you just mentioned, is that because when we look at the data, it feels like the noise are just it is to me, it feels like a high frequency signal. So do you think it's a valid solution to just for example, do some Fourier transformation and then remove the high frequencies? Or do you think that's not a valid solution here?
So in a lot of the data that we collect in our lab, that is what we do. We just base on frequency content, but there's actually no frequency correlation in the noise, and there's no frequency, there's no dominant frequencies of noise in this data that I was presenting. There are dominant frequencies of the flow fields, but they tend to be occluded by some of that noise. So even though the dominant frequencies are still evident, and that is obviously not true in the case of the correlated noise, where that sort of frequency analysis might break down because the noise would have the same frequency as the structure.
So basically, if we just simply naively remove the frequency, we may kind of mistakenly destroy the fluid data.
Exactly. And that's actually a pretty big problem, because I want to emphasize that a lot of the noise that we see is correlated to the structure, which is what is really challenging, is that these regions of interest have these large three-dimensionalities and large complexities, and they tend to get occluded by noise because the noise is attracted to those regions for physical reasons.
Wow, That's very interesting to know.
Yeah, it's really challenging.
Yeah, that's cool. Okay, now we have more questions for Professor Kara. So this one is more relevant to like the power circuit design. Is that it is really like eye-opening to see kind of this new type of clustering problem that are like very different from like our traditional notion of like a good clustering. So we're just curious, like this is a more like a beginner question. So just given the set of the pins, like is it always have a valid, feasible and desirable solution? Is there some setup that there's no feasible solution?
Fantastic question that I glossed over. And no, a solution is not guaranteed. A feasible and desirable solution is not guaranteed. In fact, for complex situations, there could be a need to eventually push one of the nets into a second parallel layer and connect the two islands through a secondary layer. That's where actually the vias come into the picture. So that's an astute observation. This is not a problem in which a solution is guaranteed. So
what do you mean second
you want to
layer?
do your best. You want to do your best with your one single layer. This is where our optimization comes in. But eventually, you can still have extra islands that need to be connected across a separate layer.
Oh, you mean like, for example, separate layer means like, for example, something like connected above or underground?
Yes.
Oh,
actually, the two islands, if they need to be on the same power at the same voltage, you need to connect them with a metal piece. And that metal piece is actually running underneath the original layer that you're seeing, which is actually going down through a via.
Wow, that's cool. And the second question is also related to this, is that are those pins are always like come from almost like a random distribution, or is there some like type of distribution that can we can leverage in order to make the strong?
So designers try to take into account, this is part of the physical design, when you actually have the device placement and all the different routing that you're going to do for your signal nets. Eventually you'll end up with a configuration in which different devices have to be distributed, laid out in this two-dimensional space. It's not always that things that need to be at the same power can be proximate to each other. So sometimes they need to be well separated in the board, and you still need to find a way to connect that. However, designers do try to anticipate this type of a situation during the device placement stage. So as they're designing their layouts, but there's so many other considerations that actually inform that device placement that, you know, the power plane proximity is just one of many different considerations. So it's not that this is the highest priority that will always be, you know, taken into account.
Thank you for this answer. And I found that we are already like a little bit over time, so I think we won't take too much time from our speakers. But if you have other questions, please feel free to reach out to them. I believe they will be happy to answer your questions. So now, thank you everyone for joining this colloquium, and let's thank our speakers again. And we also want to thank our artist, Liang Kwok, for making the poster for this week, and see you all next week.